Hello, my name is Xinyue Liang. I'm a PhD student from Division of Information Science and Engineering of KTH in Sweden. Today, I'd like to talk about our recent work, namely a low-complexity decentralized neural net with centralized equivalence using layer-wise learning. This work is co-authored by my colleagues Alireza, Mikael, and Saikat. First of all, I would like to introduce our main problem of interest. Let's consider some examples of network systems these days, like the blockchain network and the social network. There are more and more visible or invisible values lies in the data located around us. Is it possible to improve the local learning model performance by making usage of other data lies in other nodes in the network? The answer is yes. We are motivated and looking into the decentralized learning setup, which is also called data parallelism. Assuming a training dataset D, it is distributed in a communication network. This network is undirected and without any mastering node. So for a specific node M, it has its local data, XMTM, and this node M is only connected to a subset of the other nodes in the network, not necessarily all of them. And this node M has a local object function FM, and it only has direct access to information about this local objective. By collaborating with other nodes and exchange information and knowledge, the local performance can be improved. But because of social and legal risks caused by exposure of real data, it is not allowed to exchange the real data in the network system. So the goal is for all the nodes to collaborate with other nodes and exchange the model parameters to find and agree on a minimizer of the sum objective, which approximates the centralized performance as if all the data samples are available at a single node. So is it possible to realize such a centralized equivalent solution? The answer is maybe yes. When we look into this randomization-based deep neural network called self-size estimating feed-forward network. This is a multi-layer feed-forward neural network constructed in a layer-wise manner. In each layer, the model parameters are the hidden layer weights, RL and VQ. These two parameters are predefined and fixed matrices, especially RL is chosen randomly. They are predefined and will never updated in the following learning process. While L denotes the output of the nonlinearity in layer L when we feeding in input X into layer L. So it means in each layer, there is only one model parameter, output matrix OL needs to be learned. So we only solve one convex optimization problem to find the optimal solution for output matrix OL star. After OL star is obtained, we add one more layer after the current layer to construct a deeper neural network structure and making this learning process continue and repeat. So there are two advantages of SFN comparing with other traditional ANNs using backpropagation. First is its fast training time because it's feed-forward structure. Second is its simplicity, as there is only one parameter need to be learned and there's no need to calculate the hidden layer weights. So we choose SFN for realizing its decentralized setup for two reasons. First is its potential to find the global solution, also called the centralized equivalence solution, as each layer is only solving a separable convex optimization problem. The second reason is its feed-forward structure leads to a low computational complexity. So we realize this decentralized SFN in these ways. We adding up all the local objectives to construct a new problem, and this problem can be solved using a method called alternate induction method of multipliers in a distributed manner to achieve the centralized performance. We adding a constraint by forcing every local output matrix OM equals to a global O in the end. After adding this constraint, this whole problem is equivalent to a centralized problem, as if all the data samples are available at a single node. And using IDM algorithm, we can solve this problem by first introducing an auxiliary variable z, and then after some multiplications, the IDM iterations for m's node results in these three steps. The second step is a Z update. It requires a parameter averaging over all the nodes in the network. And for achieving this, it requires a sufficient times of information broadcast and exchange of all the nodes in the network. To do this, each node will broadcast its local parameters and receive model parameters from its dark neighbors and do a neighborhood parameter averaging. After sufficient times of doing this, every node in the network are traversed. So for each node, it can has a parameter averaging over all the nodes in the network. So to conclude the technical conditions of decentralized estimation for achieving a centralized solution, it can be only applied to an undirected communication network structure, and to guarantee the equivalent solution, ADM should take sufficient times of iteration to converge to the global solution. And in each iteration, it requires sufficient times of communication to obtain the network consensus. Usually, the total number of iterations is a small number, let's say within 100 iterations. And the last condition is the existence of a global clock. It means this algorithm requires synchronous communication, means that every node should activate during the same time interval and wait until the slowest node finishes processing its local data. When all the nodes get the global solution O for a specific layer L, we can add another layer after this current layer to continue the learning process and repeat the distributed algorithm in this manner. To test our proposed decentralized S7, we apply the algorithm onto an undirected network topology called circular communication network. It can control the network connectivity by changing the network degree. So in each node of this network system, we fix the S7 size, means that we fix the number of hidden neurons in each layer, and we fix the total number of layers for S7. And we predefine the random weight matrices RL and predefine BQ, and inform all of these parameters to all the nodes in the network. So in the end, every node in the network can learn the same S7 structure. The first experiment is to compare the test accuracy between centralized S7 and decentralized S7. In the table, it shows that for every dataset, the test accuracy of decentralized S7 equals to the centralized S7. For some datasets, we observe slightly higher test accuracy of decentralized S7. They are caused by early stopping issue. We observed this in the experiment, and we kept this and since it is an advantage to both avoid overfitting problem and to reduce the training time. Another thing to mention here is the choices of hyperparameters, μ's. They are the step sizes of ADMM. Since they are non-sensitive, we just choose it doing one-time parameter tuning and fix it as it is. Compared with the gradient descent step sizes, this one is much easier to tune and also reduce a lot of computational power. The second experiment is to see the behavior of the objective cost as the number of layers increases. For this experiment, we just want to show that the overall objective cost is decreasing and converging to and converges as the number of layers increases. So this results also duplicates the case of centralized case. The last experiment shows the behavior of the training time as we increase the network connectivity. When network degree equals to 1, it is a ring network. When it is equals to 10, it is a fully connected network. For both cases, the centralized solution are obtained. So the only difference is the training time. To conclude, because of the data security and the privacy issues, we propose this decentralized learning, which only exchange learning model parameters in network. And this learning algorithm reaches the same performance as the centralized case. Compared with ANNs using backpropagation, this decentralized S7 has less computational complexity in structure, and the use of ADM reduces the computational power thanks to a much easier parameter tuning process. and with sufficient times of parameter exchanges, the algorithm can provide centralized performance for a network with a high sparsity level in its connections. And our future work would be to adapt this algorithm to a synchronous communication manner. And if this can be done, we can extend this algorithm to a more relaxed communication condition. So that's all for my presentation. Thank you for your attention, and you are very welcome to ask questions or leave comments.